Assalamu alaikum. I'm Saima. Thank you so much for giving me the opportunity to showcasing the round 2 task. Let's welcome. Today we are exploring for key data structure challenges and how they apply to modern machine learning system. Let's dive in. So here's the first question: the range sum of the AVL tree, and here's the main concept of the AVL tree. It's actually a binary search tree, and in here I have tried to make the node structure, and I have fixed the pointer value, height, and the sum of the key in initial function. And next I try to update the step, and mm, it contains the insert and deletion process. So we are gonna see that how do we efficiently calculate the sum of values within a range in the AVL tree, and this is the main part where we will find our answer. In this solution, I augmented the tree, and it's not just doesn't store the value but also the sum of the all values. And in this query, we perform the modified search, and here's the comments based on the code. And the tree is if the subtree is empty, then it will return 0, and it will work in a range like left and right, and we add its value and the search both subtree. If it's less than L or the left side, then it will print the range sum, and uh, and then if it's less than the L, we'll get the right. If it's greater than the right, then we will go to the left again. And this gives us a efficient big O log n query algorithm. And here's the answer. And here's the time complexity is 0 log n. And due to ABL balancing and subtree, here's the sum updates. Now, following up the machine learning feature propagation, and in here, if every tree update must feed a model, we avoid real-time recalculations, and we will use the lazy propagation or the batch propagation, so features are recomputed only when needed, not always. And or stream, and it will change asynchronously to avoid slowing down the system, and we can scale it down with the largest scale system with incremental feature updates, parallelizing systems, pipelining, and streaming, etc. Here's the visualization layout. We have the left and right ranges. The reference is 15 and the right range is 65. This is the sum of our code. And here's the children nodes or the subtree nodes. So if we calculate our subtrees like 30 plus 20 is 50 and plus 10 is 60 and 5, then it will be 65, the range of 15 to 16 L and R. So here's our summary. We can say the key takeaway is augmented the trees for fast application, and then for the machine learning feature, we can update it with the batch updates process. And that's all for the question number 1. And next we'll jump to the question number 2. It's the B-tree for large model weights. And this is the concept of B3. And the question is contains how do we store and retrieve massive model weights? And this is the answer of our B-tree. And B-tree is a balanced tree with multi-weight search tree. Unlike a binary tree, its node can balance, and its node can hold many keys and many children, not just 2. And here's the explanation why we will choose always B-tree model. And here's the multi-key nodes and balanced, and it's disk friendly or not. It's scalable. It handles millions of records efficiently, so it's really user friendly. And then it's the code input of our B-tree model algorithm. And here I have commented it down for the PyCharm code efficiency and user readable help. And here's the application of large model weights, and it's fast readable weight by ID efficient inside and new checkpoints. If we try to explain the code, we can wrap up that this structure minimizes the tree's height, and which demonstratively reduces the number of these can reads needs to find a piece of data needs, and it needs size, and every node size and match these phases and make it incredibly disk friendly and scalable. And the second question, that we can use it on recommendation system or not. Here's the answer. The following feature vector lookups recommender systems. This is a perfect feature for vector lookups. If user and item embedding has a unique ID that we have already know, the B-tree provides fast, real-time, and retrieval of these vectors for our database of millions. And that's also we know earlier, and which is a backbone of any large scale recommendation system. So we undoubtedly can use it. There have a Python visualization code for demonstrating the layout, visual layout. Uh, Here's the range, and here there have 3 children nodes. And we can also, I have used PyCharm for as our ID. We can also use Colab and Jupyter Notebook to demonstrate the feeder. And finally, the wrap up of our B-tree model. So I can say that B-trees are the go-to for fast scalable database indexing, and it's especially for feature lookups. So it's really good for recommendation systems. And then the question number 3 is the distributed minimum spanning tree, and shortly I can call that MST. And the question is, how do we find a minimum spanning tree when our graph is distributed across many machines? So now here's the concept of our minimum spanning tree, that it connects all nodes in a weight graph and with the minimum total age post in no cycle. And here's the basic algorithm of our MSP. And the concept is initialization, local minimum age selection, the communication state, merge states, components, and the repetition system. And next, I want to show the pseudocode. It's just a pseudocode. It's not the actual code that we can be run in our ID. So there has some error, or we can say the warnings. So we used the distributed version of Borovka algorithm, and the Borovka's algorithm is a process where we can locally we can run each machine finds the cheapest edge connection and each component to another, and globally this is the best edge and share across the network. And finally the merge process, and the components connected by this edge are merged together in this process. Here's the number concept, the loop back, and next the parallel components. Here's the find smallest outage. Just I have said that the cheapest edge, and next the broadcasting chosen edge that I have already mentioned, and finally the merge connect component. We repeat this process until one single chemistry remains, and it efficiently because each machine works in parallel and only minimal data is exchanged. It not works in serially, it works parallelly. Then here's why the chemistry is so efficient. It's locally fast, only minimal information, and low network overhead merges reduces number and components exponentially. Here's the time complexity of the query, and the communication complexity is big O log V. And finally, and secondly, our question number 3, part 2, is follow up the real world machine learning scenario. The chemistries are great for feature selection in sensor networks by building on chemistry where age, weights, repeats, correlation. We can identify and keep only the most unique, non-redundant sensor and simplifying our models. So we can use it in sensor network feature selection, clustering problems like hierarchical machine learning models, and single linkage clustering and structure in data, graph-based and machine learning pipelines to use in graph simplification or communication cost minimization. And here's the look back or the visualization diagram for the according to our algorithm. Here's the step 1. The local minimum age discovery is machine 1, machine 2, and machine 3. And here's the components of our 3 machines. And in step 2, exchange and combine the minimum ages. So I have combined the minimum ages in from here. And step 3, the merging the components. I have merged the components in here and make this visualization image by me. And it's self-made visualization graph. And here's the explanation, short explanation actually. The 3 clusters like machine 1, machine B, and machine 3, ABC, and selecting the local minimum age. Their local minimum age I have taken, and this arrow indicating communication and merging into a single MST. Here's the arrows, and here's the final result of global MST state. And finally, the summary of our distributed Borovka algorithm. So I can say that distributed Borovka efficiently builds MSTs in parallel, useful for graph-based. It's a graph also. Graph-based machine learning tasks like clustering and feature selection. So I'm wrapping up the question number 3, and finally, I want to explain the question number 4, which is about the memory management for machine learning feature indices. The question contains that in a memory constrained machine learning system, how do we manage memory for feature indices to ensure latency? And there's a question that comparing between the slab allocation and the garbage collection, and which is more efficient. And here's the main concept of our 2 allocation models. The slab, I can shortly say that slab allocation is a custom or manually allocation system, kind of, and the garbage collection is a automatic collection. Whereas the explanation is the slab allocation is a pre-allocated memory block system of fixed size classes for specific object types, and the garbage collection is automatically frees unused memory and by detecting the unreadable objects at runtime. So the main comparison between the slab allocation versus the garbage collection is below, but here I'm gonna talking about the working process of the slab between them. Here's the process. Slab allocation uses holds uniform sizes objects, and when a new object is needed, allocate from the slab and feed it objects and return it same slab for reuse. But the garbage collection periodically scans memory, it identifies unused objects, and then reclaim the space. And here's the main comparison table between the slab allocation and the garbage collection, and here are our 6 features. So this is the custom allocator that pre-reserved blocks and memory slabs for a specific object type like freeze nodes. It's the slab allocation system. It is fast. It's extremely fast, not just fast. It's predictable for allocation and also the de-allocation system. And here's the performance speed. It's big O1. It's really good. And the garbage collection is slower. It also contains the fragmentation like heap fragmentation. And here's the memory constraints. Slab allocation is highly effective and allow control the memory layout consumption, but the garbage collection is less effective and it increases overhead like metadata and dead objects. It actually have so much pauses. That's the main problem in this allocation system. And then the cache locally is excellent, but it's the poor and it's variable cache memory location system uses. So memory layout can become scattered, reducing cache's heat rate and also the latency. And but both are good for different real-time systems. Like slab allocation is good for real-time and online serving, and the garbage allocation is good for offline and dynamic pipelines. Here are some pros and cons of our slab allocation and the garbage collection model's features. So the main pros of the slab allocation is it's incredibly fast, that I have called already in our previous table, that its performance speed is before 1, and it has predictable latency, and it cache friendly is excellent. I have already shown. And then there are no expected pauses. That's the main concept in our comparison system. And but there have some cons obviously in our slab allocation system. That is, it can be less flexible if object size is very great or very large. And next, the data collection. There's also have pros. Obviously, it's really easy to develop because it works dynamically and in offline. So there have no extra data issue. So it's easy to develop. And there have some cons in it. It causes stopward pauses and arises so many stopwords or pauses. That's the main problem in this allocation system. It automatically arises so many pauses. And our second part of our question, follow the machine learning system perspective. For online serving, I have already called that the slab allocation is really good for online serving system. So that's it for online serving. While predictable, low latency, responsible, and are critical, and slab allocation is the clean winner of this session. But the garbage collection is acceptable since timing variability doesn't affect user experience, but it's unpredictable and not so good for real-time prediction environment. Here's I have demonstrated a image to show the main comparison or the main problem between them. Here's the main problem is unpredictable pauses, and the slab allocation contains no pauses, and it consists low latency, and it causes high latency because of jitter and size in machine learning systems. So finally, I can say the key takeaway is to slab allocation for predictable performance, and in online machine learning serving and receive the garbage collection for offline training. It will be good. So here's the summary of my task 2, and here's the graph for my code explanation and pseudocode, I can say. So that's all for mine, and I'm wrapping up from here. So from augmented trees for fast queries, for the first queries, and secondly the B tree for scale, and thirdly the distributed algorithms for graphs, and smart memory management for the latency is slab memory allocations. And these concepts are fundamentals to building robust and efficient machine learning systems. And that's all for mine today. And thank you so much. Assalamu alaikum.